Good morning to all. I am Karina from BSc Chemistry Honors Final Year. Today's our chapter is from Clayton Greaves Farren and Weathers Organic Chemistry book. The Chemistry of Life. Life runs on chemistry, and the chemical side of biology is fascinating for that reason alone. But from the point of view of a textbook, biological chemistry is combination of structures, mechanisms, new reactions and synthesis is also an ideal revision aid. We shall create this chemistry of living things in 3 chapters. Chapter 49 introduces the basic molecules of life and explains their roles along with some of their chemistry. Chapter 50 discusses the mechanisms of biological reactions. Chapter 51 develops the chemistry of compounds produced by life, natural products. We start with the most fundamental molecules and reaction in what is called primary metabolism. Primary metabolism. It is humbling to realize that the same molecules are present in all living things, from the simplest single-cell creatures to our cells. Nucleic acid contain the genetic information of every organism and they control the synthesis of proteins. Proteins are partly structural as in connective tissue and partly functional as in enzymes. The catalyst for biological reactions. Sugars and lipids used to be the poor relations of the other two, but we now realize that as well as having a structural role in membranes, they are closely associated with proteins and have a vital part to play in recognition and transport. The chart overleaf shows the molecules of primary metabolism and the connections between them and needs some explanation. It shows a simplified relationship between the key structures emphasized in large plaque type. It shows their origins from CO2 in the first instance and picks out some important intermediates. Glucose, pyruvic acid, citric acid, acetyl coenzyme A, acetyl CoA and ribose are players on the center stage of our metabolism and are built into many important molecules. Now the structure of primary metabolism is as given. CO2 which is found in plants and that process occurs is photosynthesis. To form glucose to form sugars which is source of carbon and energy, and from sugars we made ribose. Uh, Glucose to form pyruvic, phosphate to form sugars, ribose, acetyl coenzyme, etc. The arrows used in the chart have 3 functions. Chemical reaction in usual sense. The starting material is incorporated into the product. Compound needed for the reaction but not always incorporated into the product. Compound involved in controlling a reaction not incorporated into the products. We hope that this chart will allow you to keep track of the relationship between the molecules of metabolism as you develop a more detailed understanding of them. We will now look briefly at each type of molecule. The first one is life. Life begins with nucleic acids. Nucleic acids are unquestionably top level molecules because they store our genetic information. They are polymers whose building blocks or monomers we can say are the nucleotides themselves made of 3 parts: a heterocyclic base, a sugar and a phosphate ester. A nucleoside lacks the phosphate. In the example alongside, adenine is the base, black. Adenosine is the nucleoside, base and sugar, and the nucleotide is the whole molecule, base plus sugar plus phosphate. This nucleotide is called AMP, adenosine monophosphate. Phosphates are key compounds in nature because they form useful stable linkages between molecules and can also be built up into reactive molecules by simply multiplying the number of phosphate residues. The most important of these nucleotides is also one of the most important molecules in nature, adenosine triphosphate or ATP. ATP is a highly reactive molecule because phosphates are stable anions and good leaving group. It can be attacked by hard nucleophiles at a phosphate group, usually the end one, or by soft nucleophiles at the CH2 group on the sugar. We shall see examples of both reactions soon. When a reaction is initiated in nature, very often the first step is a reaction with ATP to make the compound more reactive. This is rather like our use of TSCl to make alcohols more reactive or converting acids to acid chlorides to make them more reactive. There are 5 heterocyclic bases in DNA and RNA. In nucleic acids, there are only 5 bases, 2 sugars and 1 phosphate group possible. The bases are monocyclic pyrimidines. There are only or bicyclic purines and all are aromatic. There are only 2 purine bases found in nucleic acids, adenine, which is denoted by A, which we have already met, and guanine, G. The 3 pyrimidine bases are the simpler and they are uracil, U, thymine, T, and cytosine, C. Cytosine is found in DNA and RNA, uracil in RNA only, and thymine in DNA only. The stimulants in tea and coffee are methylated nucleic acid purines. An important natural product for most of us is a fully methylated purine present in tea and coffee, which is caffeine. Theobromine, the partly methylated version, is present in chocolate, and both caffeine and theobromine act as stimulants. Caffeine is a crystalline substance easily extracted from coffee or tea with organic solvents. It is extracted industrially with liquid CO2, or if you prefer nature's natural effervescence, to make decaffeinated tea and coffee. If we as chemists were to do those methyl groups, we should use something like MEI, but nature uses a much more complicated reagent. There is a great deal of methylating group on in living things, and the methyl groups are usually added by S-adenosyl methionine or SAM, formed by reaction of methionine with ATP. Now the reaction is given below. This is a good reaction because sulfur is a good soft nucleophile. Triphosphate is a good leaving group. Substitution at a primary carbon is easy. The product SAM is a sulfonium salt and could be attacked by nucleophiles at 3 different carbon atoms. 2 are primary center, good for SN2 reaction, but the third is the methyl group, which is even better. Many nucleophiles attack SAM in this way. In the coffee plant, theobromine is converted into caffeine with a molecule of SAM. The methylation occurs on nitrogen partly because this preserves both the aromatic ring and the amide functionality, and also because the enzyme involved brings the 2 molecules together in the right orientation for N-methylation. At this point, we should just point out something that is easy to forget. There is only one chemistry. There is no magic in biological chemistry, and nature uses the same chemical principles as we do in the chemical laboratory. All the mechanisms that you studied so far will help you to draw mechanisms for biological reactions, and most reactions that you have met have their counterparts in nature. The difference is that nature is very good at chemistry and all of us are only just learning. We still do much more sophisticated reactions inside our bodies without thinking about them that we can do outside our bodies with all the most powerful ideas available to us at the beginning of the 21st century. Nucleic acids exist in a double helix. One of the most important discoveries of modern science was the elucidation of the structure of DNA and RNA as the famous double helix by Watson and Crick in 1953. They realized that the basic structure of base sugar phosphate was ideal for a 3-dimensional coil. The structure of a small part of DNA is shown opposite. Notice that the 2' pronounced 2'. Position on the ribose ring is vacant. There is no OH group there, and that is why it is called deoxyribonucleic acid, DNA. The nucleotides link the 2 remaining OH groups on the ribose ring, and these are called 3' and 5' positions. This piece of DNA has 3 nucleotides, adenine, and thymine, and so would be called AAT for short. Each polymeric strand of DNA coils up into a helix and is bonded to another strand by hydrogen bond between the bases. Each base pairs up spatially with another base, adenine with thymine, AT, and guanine with cytosine, G to C, like this. There is quite a lot to notice about these structures. Each purine, A or G, is bonded specifically to one pyrimidine, T or C, by 2 or by 3 hydrogen bonds. The hydrogen bonds are of two kinds. One links an amine to a carbonyl group, black in the diagram, and one links an amine to an imine, green in the diagram. In this way, each nucleotide reliably recognizes another and reliably pairs with its partner. The short strand of DNA above, ATT, would pair reliably with TTA. How the genetic information in DNA is passed to proteins. In the normal structure of DNA, each strand is paired with another strand called the complementary strand because it has each base paired with its complementary base. When DNA replicates, the strands separate and a new strand with complementary structure grows alongside each. In this way, the original double helix now becomes two identical double helices and so on. This is a crude simplification of a beautiful process and you should turn to a biochemistry textbook for more details. The actual building up of a strand of DNA obviously involves a complex series of chemical reactions. The DNA is then used to build up a complementary strand of RNA, which does have the 2' hydroxyl group, and the RNA then instructs the cell on protein synthesis using 3 nucleotide codes to indicate different amino acids. Again, the details of this process are beyond the scope of this book, but the code is not. Each set of 3 nucleotides, called a triplet or codon, in a DNA molecule tells the cells to do something. Some triplets tell it to work, to start work or stop work, but most represent a specific amino acid. The code UGU in RNA tells the cell add a molecule of cysteine to the protein you are building. The code UGA tells the cell stop the protein at this point. So a bit of RNA reading UGU, UGA would produce a protein with a molecule of cysteine at the end. There are 4 bases available for DNA and so there are 4 raised to power 3 is equals to 64 different triplet codons using 3 bases in each codon. There are only 20 amino acids used in proteins, so that gives plenty of spare codons. In fact, 61 of the 64 are used as codons for amino acids and the remaining 3 are stop signals. Thus the code ATT in DNA would produce the complementary UAA and this is another stop signal. But that does not have a start signal. This signal is the same. TAC in DNA equals to AUG in RNA as that for the amino acid methionine, which you met as a component of SAM, the biological methylating agent. In other words, all proteins start with methionine, at least they are all made that way, though the methionine is sometimes removed by enzymes before the protein is released. These code letters are the same for all living things except for some minor variations in some microorganisms. AIDS is being created with modified nucleosides. Modified nucleosides have proved to be among the best antiviral compounds. The most famous anti-AIDS drug, AZT, zidovudine from GlaxoSmithKline, is a slightly modified DNA nucleoside, 3-azidothiamidine. It has an azide at C3' instead of the hydroxyl group in the natural nucleoside. Doctors are having some spectacular success at the moment against HIV and AIDS by using a combination of AZT and a much more modified nucleoside 3-TC, lamivudine, which is active against AZT-resistant viruses. This drug is based on cytosine, but the sugar has been replaced by a different heterocycle, though it is recognizably similar, especially in the spectrochemistry. The last drug to mention is acyclovir, Jovirax, the cold sore herpes treatment. Here is a modified guanosine in which only a ghost of the sugar remains. There is no ring at all and no stereochemistry. The bottom edge of the sugar ring has been done away with so that a simple alkyl chain remains. This compound has proved amazingly successful as an antiviral agent, and it is highly likely that more modified nucleosides will appear in the future as important drugs. Cyclic nucleosides and stereochemistry. We know the relative stereochemistry around the ribose ring of the nucleosides in DNA and RNA because the bases can be persuaded to cyclize onto the ring in certain reactions. Treatment of deoxythymidine with reagents that make oxygen atoms into leaving groups leads to cyclization by intramolecular SN2 reaction. The amide oxygen of the base attacks the 3' position in the sugar ring. This SN2 reaction has to happen with inversion, proving that the base and the 3' mode H group are on opposite side of the ribose ring. The cyclized product is useful too. If it is reacted with azide ion, the ring reopens with inversion in another SN2 reaction and AZT is formed. We can show that the primary alcohol is on the same side of the ring as the base by another cyclization reaction. Treatment of the related iodide with a silver first salt gives a new 7-membered ring. This reaction can happen only with the stereochemistry of starting material. In ribonucleic acid, the fact that the 2' and 3' OH groups are on the same side of the ring makes alkaline hydrolysis of such dinucleotides exceptionally rapid by intramolecular nucleophilic catalysis. The alkali removes a proton from the 2' group which cyclizes onto the phosphate link, possible only if the ring fusion is cis. The next reaction involves breakdown of the pentacovalent phosphorus intermediate to give a cyclic phosphate. One nucleoside is released by this reaction and the second follows when the cyclic phosphate is itself cleaved by alkali. The simplest cyclic phosphate that can be formed from a nucleotide is also important biologically as it is a messenger that helps to control such processes as blood clotting and acid secretion in the stomach. It is cyclic AMP CAMP formed enzymatically from ATP by nucleophilic displacement of pyrophosphate by the 3' OH group. Proteins are made of amino acids. The molecules of methionine, which we met as a component of SAM, is a typical amino acid of the kind present in proteins. It is the starter unit in all proteins and is joined to the next amino acid by an amide bond. In general, we could write. Now we can add the next amino acid using its correct codon, but we want to show the process in general, so we shall use the general structure in the margin. All amino acids have the same basic structure and differ only in the group R. Both structures are the same and have the same stereochemistry. The process then continues with more amino acids added in turn to the right hand end of the growing molecule. A section of the final protein drawn in a more realistic conformation might look like this. The basic skeleton of protein zigzags up and down in the usual way. The amide bonds shown in black are rigid because of the amide conjugation and are held in the shape shown. Each amino acid may have a different substituent R1, R2, R3, etc. or some may be the same. A catalog of the amino acids. So what groups are available when proteins are being made? The simplest amino acid glycine has no substituents except hydrogen and is the only amino acid that is not chiral. 4 other amino acids have alkyl groups without further functionality. The next table gives their structures together with 2 abbreviations widely used for them. The 3-letter code, which has nothing to do with the codon in DNA, is almost self-explanatory, as are the 1-letter codes in this group. But some of the 1-letter codes for other amino acids are not so obvious. These amino acids form hydrophobic, water-repelling, non-polar regions in proteins. There are 3 more of this kind with special roles. Phenylalanine and tryptophan have aromatic rings, and though they are still hydrophobic, they can form attractive pi stacking interaction with other aromatic molecules. Enzyme catalyzed hydrolysis of proteins often happens next to one of these residues. Proline is very special. It has its amino group inside a ring and has a different shape from all the other amino acids. It appears in proteins where a band or a twist in the structure is needed. The rest of the amino acids have functional groups of various kinds, and we shall deal with them by function. The simplest have hydroxyl groups, and there are three of them, two alcohols and a phenol. Serine in particular is important as a reactive group in enzymatic reactions. It is a good nucleophile for carbonyl groups. Next come the two compounds we have already met, the sulfur containing cysteine and methionine. Cysteine has a thiol group and methionine has sulfide. These are very important in protein structure. Methionine starts off the synthesis of every new protein as its N-terminal amino acid, while cysteine forms SS bases linking two parts of a protein together. These disulfide links may be important in holding the three-dimensional shape of the molecule. Cysteine and hair dressing. Thiols RSH are easily oxidized by air. For example, two disulfides RSSR. This chemistry of cysteine is used by hairdressers to give perms or permanent waves. The hair proteins are first reduced so that any disulfide cysteine to cysteine cross links within each strand are reduced to thiols. Then the hair is styled and the final stage is the set when the hair is oxidized so that disulfide cross links are established to hold its shape for a good time. The disulfide resulting from cross-links between the thiol groups of cysteine is known as cysteine. Beware of confusing the names. The amino acids with a second amino group are important because of their basicity and they are vital to the catalytic activity of many enzymes. Histidine has a pKa very close to neutrality 6.5 and can function as an acid or a base. Lysine and arginine are much more basic but are normally protonated in living things. An extra column in this table gives the pKa of the extra amino groups. Essential amino acids. If you saw Jurassic Park, you may recall that the fail-safe device was the lysine option. The dinosaurs were genetically modified so as to need lysine in their diet. The idea was that they would die unless lysine was provided by their keepers. Lysine was a good choice as it is one of the essential amino acids for humans. If we are not giving it in our diet, we die. Of course, any normal diet, including the human beings eaten by the escaped dinosaurs, would also contain plenty of lysine. The other essential amino acids for humans are HIS, LLE, LEU, MET, PHE, THR, TRY and VAL, which is valine. Finally, we come to the acidic amino acids, those with an extra carboxylic acid group. We are going to include their amides too as they also occur in proteins. This group is again very much involved in the catalytic activity of enzymes. The two acids have pKas for the extra CO2H group of about 4.5. Sometimes it is not known whether the acids or their amides are present and sometimes they are present interchangeably. Aspartic acid and or asparagine has the codes ASX or B and B, while glutamic acid or glutamine is GLX or Z. Now perhaps you can see that a protein is an assembly of many different kinds of groups attached to a polyamide backbone. Some of the groups are purely structural, some control the shape of the protein, some help to bind other molecules, and some are active in chemical reactions. Most amino acids are readily available to chemists. If proteins are hydrolyzed with say concentrated HCl, they are broken down into their amino acids. This mixture is tricky to separate, but the acidic ones are easy to extract with base, while the aromatic ones crystallize out easily. Amino acids combine to form peptides and proteins. In nature, the amino acids are combined to give proteins with hundreds or even thousands of amino acids in each one. Small assemblies of amino acids are known as peptides and the amide bond that links them is called a peptide bond. One important dipeptide is the sweetening agent aspartame, whose synthesis was discussed in chapter 25. It is composed and made of the amino acid aspartic acid ASP and the methyl ester of phenylalanine. Only this enantiomer has a sweet taste, and it is very sweet indeed, about 160 times as sweet as sucrose. Only a tiny amount is needed to sweeten drinks, and so it is much less fattening than sucrose and is safe because it is degraded in the body to ASP and PHE, which are there in larger amounts anyway. An important tripeptide is glutathione. So important is this compound that it is present in almost all tissues of most living things. It is the universal thiol that removes dangerous oxidizing agents by allowing itself to be oxidized to a disulfide. Glutathione is not quite a simple tripeptide. The left-hand amino acid is normal glutamic acid, but it is joined to the next amino acid through its gamma CO2H group instead of the more normal alpha CO2H group. The middle amino acid is the vital one for the function cysteine with a free SH group. The C-terminal acid is glycine. Thiols are easily oxidized to disulfides, as we have already seen in our discussion on hairdressing. Though the redox chemistry of glutathione is a matter of life or death and not merely a bad hair day. And glutathione sacrifices itself if it meets an oxidizing agent. Later the oxidized form of glutathione is reduced back to the thiol by reagents we shall meet in the next chapter, NADH, etc. If we imagine that the stray oxidizing agent is a peroxide, say H2O2, we can draw a mechanism to show how this can be reduced to water as glutathione, represented as RSH, is oxidized to a disulfide. Paracetamol overdoses. Paracetamol is a popular and safe analgesic if used properly, but an overdose is insidiously dangerous. The patient often seems to recover only to die later from liver failure. The problem is that paracetamol is metabolized into an oxidizing compound that destroys glutathione. Glutathione detoxifies this oxidizing agent by a most unusual mechanism. The unstable hydroxylamine loses water to give a reactive quinone imine that is attacked by glutathione on the aromatic ring. The adduct is stable and safe, but for every molecule of paracetamol, one molecule of glutathione is consumed. There is no problem if a normal dose is taken. There is plenty of glutathione to deal with that. But if an overdose is taken, all the glutathione may be used up and irreversible liver damage occurs. Glutathione also detoxifies some of the compounds we have earlier described as very dangerous carcinogens, such as Michael acceptors and 2,4-dinitrohalobenzenes. In both cases, the thiol acts as a nucleophile for these electrophiles. Most of the time, there is enough glutathione present in our cells to attack these poisons before they attack DNA or an enzyme. The toxin is now covalently bound to glutathione, and so it is no longer electrophilic. It is harmless and can be excreted. More glutathione will be synthesized from glutamic acid, cysteine and glycine to replace that which is lost. Proteins are nature's chemical laboratories. Longer peptides are called proteins, though where exactly the boundary occurs is difficult to say. The structure of hormone insulin. Many diabetics lack this hormone and must inject themselves with it daily. Was deduced in the 1950s by Sanger. It has two peptide chains, one of 21 amino acid and one of 30, linked by 3 disulfide bases, just like the links in oxidized glutathione. This is a very small protein. Enzymes are usually bigger. One of the smaller enzymes, ribonuclease, which hydrolyzes RNA from cows, has a chain of 124 amino acids with 4 internal disulfide bases. The abundance of the various amino acids in this enzyme is given in this table. There are 48 structural and cross-linking amino acids concerned with the shape of the protein, but over half of the amino acids have functional groups sticking out of chain, amino hydroxy acid groups and the like. In fact, the enzyme uses only a few of these functional groups in the reaction. It catalyzes the hydrolysis of RNA, probably only 2 histidines and 1 lysine, but it is typical of enzymes they have a vast array of functional groups available for chemical reactions. Below is part of the structure of ribonuclease surrounding one of the catalytic amino acid, HIS12. There are 7 amino acids in this sequence. Everyone is different and everyone has a Functionalized side chain. This is part of a run of 10 amino acids between PHE8 and ALA19. This type of peptide has 6 different functional groups, 2 acids, one each of amide, guanidine, imidazole, sulfide and alcohol, available for chemical reactions. Only the histidine is actually used. One reason for disease is that enzymes may become overactive and it may be necessary to design specific inhibitors for them to treat the disease. Angiotensin converting enzyme ACE is a zinc dependent enzyme that cleaves two amino acids off the end of angiotensin I to give angiotensin 1 to give angiotensin 2, a protein that causes blood pressure to rise. It is necessary in some situations for our blood pressure to rise when we stand up, for instance. But too much too often is a very bad thing, leading to heart attacks and strokes. Captopril is a treatment for high blood pressure called an ACE inhibitor because it works by inhibiting the enzyme. It is a dipeptide mimic having one natural amino acid and something else. The something else is an SH group, replacing the NH2 group in the natural dipeptide. Captopril binds to the enzyme because it is like a natural dipeptide but inhibits the enzyme because it is not a natural dipeptide. In particular, the SH group is a good ligand for ZN2. Many people are alive today because of this simple deception practiced on an enzyme. Structural proteins must be tough and flexible. In contrast with the functional enzymes, there are purely structural proteins such as collagen. Collagen is the tough protein of tendons and is present in skin, bone and teeth. It contains large amounts of glycine. Every third amino acid is glycine. Proline and hydroxyproline. Again, about a third of amino acids are either pro or HYP hype. In the enzyme above, there were only 3 glycines and 4 prolines and no hydroxyproline at all. Hydroxyproline is a specialized amino acid that appears almost nowhere else, and along with proline, it establishes a very strong triply coiled structure for collagen. The glycine is necessary as there is no room in the inside of the triple coil for any large amino acid. Functionalized amino acids are rare in collagen. Hydroxyproline and scurvy. Hydroxyproline is a very unusual amino acid. There is no genetic codon for the insertion of HYP into a growing protein because collagen is not made that way. The collagen molecule is first assembled with pro where hype ends up. Then some proline residues are oxidized to hydroxyproline. This oxidation requires vitamin C and without it, collagen cannot be formed. This is why vitamin C deficiency causes scurvy. The symptoms of scurvy, teeth falling out, sores, blisters, are caused by the inability to make collagen. Proteins are enormously diverse in structure and function, as we will be looking at a few of their reactions in the next chapter. Sugars, just energy sources. Sugars are the building blocks of carbohydrates. They used to be thought of as essential but rather dull molecules, whose only functions were the admittedly useful provision of energy and cell wall construction. We have already noted that ribose plays an intimate role in DNA and RNA structure and function. More recently, biochemists have realized that carbohydrates are much more exciting. They are often found in intimate association with proteins and are involved in recognition of one protein by another and in an addition processes. That may not sound very exciting, but take 2 examples. How does a sperm recognize the egg and penetrate its wall? The sperm actually binds to a carbohydrate on the wall of the egg in what was the first event in all of our lives. Then how does a virus get inside a cell? If it fails to do so, it has no life. Viruses depend on host cell to reproduce. Here again, the recognition process involves specific carbohydrates. One of the ways in which AIDS is being tackled with some success is by a combination of the antiviral drugs we met earlier in this chapter with HIV protease inhibitor drugs, which aim to prevent recognition and penetration of cells by HIV. We now know that many vital activities as diverse as healing, blood clotting, infection, prevention of infection, and fertilization all involve carbohydrates. Mysterious compounds such as silyl, allyl, Lewis X, unknown a few years ago, are now known to be vital to our health and happiness. Far from being dull, carbohydrates are exciting molecules and our future depends on them. It is worthwhile to spend some time exploring their structure and chemistry. Sugars normally exist in cyclic forms with much stereochemistry. The most important sugar is glucose. It has a saturated six-membered ring containing oxygen and it is best drawn in a chair conformation with nearly all the substituents equatorial. It can also be drawn reasonably as a flat configurational diagram. We have already met one sugar in this chapter, ribose, because it was part of structure of nucleic acids. This sugar is a five-membered saturated oxygen heterocycle with many OH groups. Indeed, you can define a sugar as an oxygen heterocycle with every carbon atom bearing an oxygen-based functional group, usually OH, but alternatively C double bond O. Both our drawings of glucose and ribose show a number of stereogenic centers and one center undefined. The OH group is marked with a wavy line. This is because one center in both sugars is a hemiacetal and therefore the molecule is in equilibrium with an open chain hydroxyaldehyde. For glucose, the open chain form is this. When the ring closes again, any of the OH groups could cyclize onto the aldehyde, but there is no real competition. The six-membered ring is more stable than any of the alternatives, which could have 3, 4, 5 or 7-membered rings. Check for yourself. However, with ribose, there is a reasonable alternative. The most important sugars may exist in an open chain form as a 5-membered oxygen heterocycle called a furanoside after the aromatic furan, or a 6-membered oxygen heterocycle called a pyranoside after the compound pyran. From triose to glucose requires doubling the number of carbon atoms. We will return to that in a moment, but let us start from the beginning. The simplest possible sugar is glyceraldehyde, a 3-carbon sugar that cannot form a cyclic hemiacetal. Glyceraldehyde is present in cells as its phosphate, which is in equilibrium with dihydroxyacetone phosphate. This looks like a complicated rearrangement, but it is actually very simple. The two compounds have a common enol through which they interconvert. Glyceraldehyde is an aldehyde sugar or aldose, and dihydroxyacetone is a keto sugar or ketose. That ending "ose" just refers to a sugar. These two molecules combine to form the 6-carbon sugar. Fructose in living things, and this reaction is a key step in the synthesis of organic compounds from CO2 in plants. When we come to the 4-carbon sugar or tetroses, two are important. They are distereoisomers called erythrose and threose. You can see from this series that each aldose has N2 stereogenic centers in its carbon chain, where N is the total number of carbon atoms in that chain. We shall take a longer look at the stereochemistry and reactions of glucose and the important ketohexose fructose. These two are often found together in cells and are combined in the same molecule as sucrose, ordinary sugar. In this molecule, glucose appears as a pyranose 6-membered ring and fructose as a furanose 5-membered ring. They are joined through an acetal at what were hemiacetal position, and sucrose is a single distereoisomer. Sugars can be fixed in one shape by acetal formation. This is the simplest way to fix glucose in the pyranose form. Any alcohol, methanol for example, gives an acetal, and remarkably the acetal has an axial OR group. Acetal formation is under thermodynamic control, chapter 14. So the axial compound must be the most stable. This is because of the anomeric effect, so called because this carbon atom is called the anomeric position and the acetal distereoisomers are called the anomers. This effect is a bonding interaction between the axial lone pair on the oxygen atom in the ring and the sigma star orbital of OMe group. The formation of acetals allows a remarkable degree of control over the chemistry of sugars. Apart from the single glucoside acetal we have just seen, there are 3 important acetals worth understanding because of the way in which they illustrate stereoelectronic effects. The interplay of stereochemistry and mechanism. If we make an acetyl from methyl glucoside, we get a simple single compound as a single stereoisomer. The new acetyl could have been formed between any of the adjacent OH groups in the starting material, but it chose the only pair, the black OH groups, to give a 6-membered ring. The stereochemistry of glucose is such that the new 6-membered ring is transfused on the old, so that a beautifully stable all-chair bicyclic structure results, with the phenyl group in an equatorial position in the new chair acetyl ring. It doesn't matter which OH group adds to benzaldehyde first, because acetyl formation is under thermodynamic control and this product is the most stable possible acetyl. Acetyls found from sugars and acetone have a quite different selectivity. For a start, cyclic acetyls of acetone prefer to be 5 rather than 6-membered rings. In a 6-membered ring, one of the acetone's methyl groups would have to be axial, so the 5-membered ring is preferred. A 5 by 5 or 5 by 6 ring fusion is more stable if it is cis, and so acetone acetyls acetonides form preferentially from cis 1,2 diols. Glucose has no neighboring cis hydroxyls in the pyranose form, but in the furanose form it can have 2 pairs. Formation of an acetyl with acetone fixes glucose in the furanose form. This is all summarized in the scheme below. The open chain form of glucose is in equilibrium with both pyranose and furanose forms by hemiacetal formation with the black and green OH groups respectively. Normally the pyranose form is preferred, but the furanose form can form a double acetyl with acetone. One acetyl having cis-fused 5 by 5 rings and the other being on the side chain. This is the product. If we want to fix glucose in the open chain form, we must make an acetyl of quite a different kind using a thiol instead of an alcohol, an aldehyde or a ketone. The thiol combines with the aldehyde group of the open chain form to give a suitable dithioacetal. The dithioacetal is evidently more stable than the alternative hemiacetals or monothioacetals that could be formed from the pyranose and furanose forms. Sugar alcohols are important in food chemistry. Another reaction of the open chain form of sugars is reduction of the aldehydic group. This leads to the series of polyols having an OH group on each carbon atom. We will use mannose as an example. Mannose is a distereoisomer of glucose having one axial OH group marked in black, and like glucose is in equilibrium with the open chain form. If we redraw the open chain form in a more realistic way, then reduce it with NaBH4. The product is mannitol, whose symmetry is interesting. It has C2 symmetry with the C2 axis at right angles to the chain and marked with the orange dot. This simplification of stereochemistry results because the two ends of the sugar both now have CH2OH groups, so that the possibility of C2 and planar symmetry arises. If we look at the two 4-carbon sugars, we can establish some important stereochemical correlations. Threose is reduced to 3-tol, which has the C2 axis like that of mannitol. C2 means that the axis of symmetry is twofold. Rotating 180 degree gives the same structure. Erythrose, on the other hand, reduces to erythritol, which is not chiral. This may not be obvious in the normal drawing, which has a center of symmetry, but rotation around the central carbon-carbon bond clearly shows the plane of symmetry. Neither plane nor center of symmetry may be present in a chiral molecule, but a C2 axis is allowed. The important correlation is that threose is reduced or oxidized to chiral compounds. The oxidation product is tartaric acid, while erythrose is reduced or oxidized to meso compounds. This may help you to remember the labels erythro and threose should you need to. In the pentoses and hexoses, there are again sugars that are reduced to meso alcohols, and some of that are reduced to C2 symmetric alcohols. The C5 sugar xylose has the same stereochemistry as glucose from C2 to C4, but lacks the CH2OH group at C6. Xylose is reduced to the meso alcohol xylitol. This alcohol is more or less as sweet as sugar, and a xylose, which is not sweet, can be extracted in large quantities from waste products such as sawdust, or corn cobs. Xylitol is used as a sweetener in foods. There is an advantage in this. Though we can digest xylitol, so it is fattening. The bacteria on teeth can note so that xylitol does not cause tooth decay. By careful manipulation of protecting groups such as acetals and reactions such as reduction and oxidation, it is possible to transform sugars into many other different organic compounds, retaining the natural optical activity of the sugars themselves. As some sugars are also very cheap, they are ideal starting points for the synthesis of other compounds and are widely used in this way. Sucrose and glucose are very cheap indeed, probably the cheapest optically active compounds available. Here are the relative to glucose is equals to 1 prices of some other cheap sugars. Chemistry of ribose from sugars to nucleotides. We have said little about selective reaction of pentoses, so we shall turn now to the synthesis of nucleotides such as AMP. In nature, ribose is a phosphorylated on the primary alcohol to give ribose 5-phosphate. This is of course an enzyme catalyst reaction, but it shows straightforward chemoreactivity such as we should expect from a chemical reaction. The second step is a pyrophosphorylation at the anomeric position to give PRPP. Only one dry stereoisomer is produced, so presumably the two anomers interconvert rapidly and only the one isomer reacts under control by the enzyme. This selectivity would be very difficult to achieve chemically. Now the stage is set for an SN2 reaction. The nucleophile is actually the amide group of glutamine, but the amide is hydrolyzed by the same enzyme in the same reaction, and the result is as if a molecule of ammonia had done on the SN2 reaction, displacing the pyrophosphate from the anomeric position. An NH2 group is introduced, which is then built into the purine ring system in a series of reactions involving simple amino acids. These reactions are too complex to describe here. By contrast, if a pyrimidine is to be made, nature assembles a general pyrimidine structure first and adds it in one step to the PRPP molecule, again in an SN2 reaction using a nitrogen nucleophile. This general nucleotide orotidylic acid can be converted into the other pyrimidine nucleophiles by simple chemistry. The chemical version, protection all the way. In a chemical synthesis work that led to Alexander Lord Todd's Nobel Prize, there are rather different problems. We cannot achieve the remarkable selectivity between the different OH groups achieved in nature, so we have to protect any OH group that is not supposed to react. We also prefer to add preformed purines and pyrimidines to a general electrophile derived from ribose. The first step is to form the acetate ester from all the OH groups. Since ribose is a rather unstable to acetylation conditions, the methyl glucoside, which is formed under very mild conditions, is used. This fixes the sugar in the furanose form. Now the tetraacetate can be made using acetic anhydride in acidic solution. All of the OH groups react by nucleophilic attack on the carbonyl group of the anhydride with retention of configuration except for the anomeric OH, which esterifies by the SN1 mechanism. This of course epimerizes the anomeric center, but the crystalline diastereomer shown can be isolated easily. Now the anomeric center can be activated towards nucleophilic attack by replacement of acetate by chloride. This is again an SN1 reaction and produces a mixture of chlorides. The other esters are stable to these conditions. Replacement of the chlorine by the purine and pyrimidine base is sometimes quite tricky, and silver or silyl derivatives are often used. Lewis acid catalysis is necessary to help the chloride ion live in this SN1 reaction. We shall avoid detailed technical discussion and simply draw the adenosine product from a general reaction. Now we need to remove the acetate and put a phosphate specifically on the 5 position. The acetate can be removed with retention by ester hydrolysis, and we already know how to protect the 2 OH and 3 OH groups. They are cis to each other, so they will form an acetal with acetone, leaving the 5 OH group free. Putting on the phosphate is tricky too, and more protection is necessary. This phosphorus compound with one chloride as leaving group and two benzyl esters as protecting groups proved ideal. The benzyl esters can be removed by hydrogenation and the acetal by treatment with a dilute acid to give AMP. The chemical synthesis involves a lot more selective manipulation of functional groups, particularly by protection, than is necessary in the biological synthesis. However, this synthesis paved the way to the simple synthesis of nucleotides and polynucleotides carried out routinely nowadays. The usual method is to build short runs of nucleotides and then let the enzymes copy them, a real partnership between biology and chemistry. Glucosides are everywhere in nature. Many alcohols, thiols, and amines occur in nature as glycosides. That is as OS or N-acetals at the anomeric position of glucose. The purpose of attaching these compounds to glucose is often to improve solubility or transport across membranes to expel a toxin from the cell. For example, sometimes glucose is attached in order to stabilize the compound so that glucose appears as nature's protecting group rather as a chemist would use a THP group. O-glycosides occur in immense variety with glucose and other sugars being joined to the OH group of alcohol and phenol to form acetals. The stereochemistry of these compounds is usually described by the Greek letters alpha and beta. If the OR bond is down, we have an alpha glycoside. If up, a beta glycoside. An attractive example is the pigment of red roses, which is an interesting aromatic oxygen heterocycle, an anthocyanidine. Two of the phenolic OH groups are present as beta glycosides. Protect yourself from cancer with green vegetables, S-glycosides. We will take an important series of S-glycosides for further chemical discussion in this chapter. It is clear that there are special benefits to health in eating broccoli and Brussels sprouts because of their potent sulfur-containing anti-cancer compounds. These compounds are unstable isothiocyanates and are not in fact present in the plant but are released on damage by, for example, cutting or cooking when a glycosidase, an enzyme which hydrolyzes glycosides, releases the sulfur compound from its glucose protection. A simple example is sinistridine. When a glycosidase enzyme cleaves an O-glycoside, we should expect a simple general acid catalyzed first step followed by fast addition of water to the intermediate oxonium ion. Essentially the same mechanism as is shown by the chemical reaction. The S-glycosides of the sinistridine group start to hydrolyze in the same way. The sulfur atom is the better leaving group but when it leaves as an anion, so worse than oxygen when the hydrolysis occurs in acidic conditions, CP000, and these anions are additionally stabilized by conjugation. The next step is very surprising. A rearrangement occurs rather similar to the Bachmann rearrangement in which the alkyl group migrates from carbon to nitrogen and an isocyanate is formed. Sinistridine occurs in mustard and horseradish and it is the release of the allyl isocyanate that gives them their hot taste. When mustard powder is mixed with water, the hot taste develops over some minutes as sinistridine is hydrolyzed to the isothiocyanate. The S-glycoside in broccoli and Brussels sprouts that protects from cancer is somewhat similar but has one more carbon atom in the chain and contains a sulfoxide group as well. Hydrolysis of the S-glycoside is followed by the same rearrangement, producing a molecule called sulforaphane. Sulforaphane protects against cancer-causing oxidants by reducing the formation of a reduction enzyme. Compounds derived from sugars. Vitamin C. Nature makes some important compounds from simple sugars. Vitamin C, ascorbic acid, is one of these. Like glutathione, it protects us from stray oxidants as well as being involved in primary redox pathways. We mentioned earlier its role in collagen synthesis. Its reduced and oxidized forms are these. Vitamin C looks very like a sugar as it has 6 carbon atoms, each having an oxygen atom as substituent as well as an oxygen heterocycle, and it is no surprise that it is made in nature from glucose. We shall give just an outline of the process which appropriately involves a lot of oxidation and reduction. The first step takes the primary alcohol of glucose to a carboxylic acid known as glucuronic acid. Next comes a reduction of the mast aldehyde to give gulonic acid. Both reactions are quite reasonable in terms of laboratory chemistry. It is pretty obvious what will happen to this compound as it is an open chain carboxylic acid 5 OH groups with 5 OH groups. One of the OH group will cyclize onto the acid to form a lactone. Kinetically, the most favorable cyclization will give a 5-membered ring, and that is what happens. Now we are getting quite close to ascorbic acid, and it is clear that oxidation must be the next step so that the double bond can be inserted between C2 and C3. This looks a strange reaction, but it is really quite logical. One of the secondary OH groups must be oxidized to a ketone. This is the 2OH group, and then the resulting ketone can simply enolize to give ascorbic acid, inositols. We have already discussed the widespread sugar alcohols such as mannitol, but more important compounds are cyclic sugar alcohols. Having a carbocyclic ring, cyclitols, the most important is inositol, which controls many aspects of our chemistry that require communication between the inside and outside of the cell of a cell. Inositol 1,4,5 triphosphate (IP3) can open calcium channels in cell membranes to allow calcium ions to escape from the cell. Inositol is made in nature from glucose 6-phosphate by an aldol reaction that requires preliminary ring opening and selective oxidation. This would be tricky in the lab without protecting groups. The resulting ketone can be enolized on the phosphate side and added to the free aldehyde group to form the cyclohexane ring. We can draw the mechanism for the aldol reaction easily if we first change the conformation. Finally, a stereochemically controlled reduction to give the axial alcohol. This would be the stereoselectivity expected with NaBH4. For example, see chapter 18 gives myo-inositol. The number and position of phosphate esters can be controlled biochemically. This control is vital in the biological activity and would be difficult in the laboratory. Learning from nature the synthesis of inositols. If we wish to devise a chemical version of biosynthesis of inositols, we need to use cleverly devised protecting groups to make sure that the right OH group is oxidized to a ketone. We can start with glucose trapped in its furanose formed by a double acetone acetal as we discussed above. The one remaining OH group is first blocked as a benzyl ether. Next, one of the acetals is hydrolyzed under very mild conditions and the primary alcohol is protected as a trityl ether. This is an SN1 reaction with an enormous electrophile, so big that it goes on primary alcohols only. Notice that each oxygen atom in this molecule of protected glucose is now different. Only the OH at C5 is free and its time has come. It can now be oxidized using a Swern procedure with dimethyl sulfoxide as the oxidant. Now we can stripe away the protecting groups one by one, and it is instructive to see how selective these methods are. The trityl group comes off in aqueous acetic acid by another SN1 reaction in which water captures the triphenylmethyl cation and the benzyl group is removed by hydrogenolysis, hydrogen gas over a 10% palladium on charcoal catalyst in ethanol. Finally, the acetone acetal is removed by acid hydrolysis. Because free sugars are difficult to isolate, it is convenient to use an acidic resin known as Dovax. The resin whose polymeric structure is discussed in chapter 52 can simply be filtered off at the end of the reaction and the solid product is isolated by lyophilization. Evaporation of water at low pressure below freezing point. The yield is quantitative. All of the hydroxyl groups are now free except the one tied up in the hemiacetal, and that of course is in equilibrium with the open chain hydroxyaldehyde as we have already seen. Treatment of this free glucose ketone with aqueous NaOH gives the ketone of myo-inositol as the major product together with some of other distereoisomers. The simplest explanation of this result is that the chemical reaction has followed essentially the same course as the biological one. First, the hemiacetal is opened by the base to give the open chain ketoaldehyde. Rotation about a CC bond allows a simple aldol condensation between the enolate of the ketone as nucleophile and the aldehyde as electrophile. The enolate must prefer to attack the aldehyde in the same way as in the biological reaction to give the all equatorial product as the conformational drawing shows. The arrangement of the enolate in the aldol reaction itself will be the same as in the cyclization of the phosphate above. As in many other cases, by improving the rate and perfecting the stereoselectivity, the enzyme makes much better a reaction that already works. Most sugars are embedded in carbohydrates. Before we leave the sugars, we should say a little about the compounds formed when sugars combine together. These are saccharides, and they have the same relationship to sugars as peptides and proteins have to amino acids. We have met one simple disaccharide, sucrose, but we need to meet some more important molecules. One of the most abundant compound in nature is cellulose, the structural material of plants. It is a glucose polymer and is produced in simply enormous quantities, about 10 raised to power 15 kilogram per year. Each glucose molecule is joined to the next through the anomeric bond C1 and the other end of the molecule C4. Here is that basic arrangement. Notice that the anomeric bonds are all equatorial. This means that the cellulose molecule is linear in general outline. It is made rigid by extra hydrogen bonds between the three OH groups and the ring oxygen atoms like this. The polymer is also coiled to increase stability still further. All this makes cellulose very difficult to hydrolyze, and humans cannot digest cellulose as we do not have the necessary enzymes. Only ruminants such as cows, whose many stomachs harbor some helpful bacteria, can manage it. Amino sugars add versatility to saccharides. To go further in understanding the structural chemistry of life, we need to know about amino sugars. These molecules allow proteins and sugars to combine and produce structures of remarkable variety and beauty. The most common amino sugars are N-acetyl glucosamine and N-acetyl galactosamine, which differ only in stereochemistry. The hard outer skeleton of insects and shellfish contains chitin, a polymer very like cellulose but made of acetyl glucosamine instead of glucose itself. It coils up in a similar way and provides the toughness of crab shells and beetle cases. Ordinary cell membranes must not be so tough as they need to allow the passage of water and complex molecules through channels that can be opened by molecules such as inositol phosphates. These membranes contain glycoproteins, proteins with amino sugar residues attached to asparagine, serine, or threonine in the protein. The attachment is at the anomeric position so that these compounds are O or N glycosides of the amino sugars. Here is N-acetyl galactosamine attached to an asparagine residue as an N glycoside. The cell membrane normally contains less than 10% of sugars, but these are vital to life. Because the sugars are covered with very polar group OH and amide, they prefer to sit outside the membrane in the aqueous extracellular fluid rather than within the non-polar membrane itself. When two cells meet, the sugars are the first things they see. We cannot go into the details of the biological processes here, but even the structure of the saccharides dangling from the cell are very interesting. They contain amino sugars, again particularly N-acetyl glucosamine and N-acetyl galactosamine, and they are rich in mannose. In addition, they are usually branched at one of the mannose residues that is joined to the other mannoses on one side and to one glucosamine on the other. The glucosamine leads back eventually to the protein through a link to asparagine like the one we have just seen. The two mannoses are linked to most sugars at positions marked by the green arrows and provide the recognition site. The structure below is a typical branch point. Mannose is another glucose distereoisomer and has one axial OH group at C2. You should begin to see from structures like these just how versatile sugar molecules can be. From just 4 sugars, we have constructed a complex molecule with up to 13 possible link sites. With more sugars added, the possibilities become enormous. It is too early to say what medical discoveries will emerge from these molecules. But one that is likely to be potent is sialyl Lewis X. This tetrasaccharide is also branched, but it contains a different type of molecule, a C9 sugar with a CO2H group called sialic acid. Sialic acid has the CO2H group at the anomic position, a typical N-acetyl group, and a unique side chain in green with 3 more OH groups. Siallyl Lewis X has sialic acid at the end of a branched sugar chain. The branch point is the familiar N-acetyl glucosamine through which the molecule is eventually linked to the glycoprotein. The remaining sugars are galactose, a distereoisomer of glucose, and a sugar we have not seen before, fucose. Fucose often appears in saccharides of this kind, and this is a 6 carbon sugar without a primary OH group. It is like galactose with Me instead of CH2OH. Sialyl Lewis X can also form a stable complex with calcium ions as the diagram shows, and this may be vital to its activity. It is certainly involved in leukocyte addition to cells and is therefore vital in the prevention of infection. Lipids. Lipids, fats, are the other important component of cell membranes. Along with cholesterol, also a component of the cell membrane, they have acquired a bad name, but they are nonetheless essential to the function of membranes as selective barriers to the movement of molecules. The most common types of lipids are esters of glycerol. Glycerol is just propane 1,2,3-thiol, but it has interesting stereochemistry. It is not chiral as it has a plane of symmetry, but the two primary OH groups are anisotropic. If one of them is changed by esterification, for example, the molecule becomes chiral. Natural glycerol phosphate is such an ester and it is optically active. A typical lipid in foodstuffs is the triester formed from glycerol and oleic acid, which is the most abundant lipid in olive oil. Oleic acid is a monounsaturated fatty acid. It has one jet double bond in the middle of the C18 chain. This bond gives the molecule a marked kink in the middle. The compound actually present in olive oil is the triester, also kinked. Oil and water do not mix. The lipid has more or less the conformation shown in the diagram with all the polar ester groups at one end and the hydrocarbon chain bunched together in a non-polar region. Oil and water do not mix, it is said, but triglyceride lipids associate with water in a special way. A drop of oil spreads out on water in a very thin layer. It does so because the ester groups sit inside the water and the hydrocarbon side chains stick out of the water and associate with each other. When triglycerides are boiled up with alkali, the esters are hydrolyzed and a mixture of carboxylate salt and glycerol is formed. This was how soap was made. Hard soap was the sodium salt and soft was soap the potassium salt. When a soap is suspended in water, the carboxylate groups have a strong affinity for the water and so oily globules or micelles are formed with the hydrocarbon side chain inside. It is these globules that remove greasy dirt from you or your clothes. Nature uses thiol esters to make lipids. The repulsion between molecules having oily or aqueous properties is the basis for membrane construction. The lipids found in membranes are mostly based on glycerol phosphate and normally contain three different side chains: one saturated, one unsaturated, and one very polar. The saturated chain is added first at C1 of glycerol phosphate. The reagent is a thiol ester called acyl coenzyme A, whose full structure you will see in the next chapter. This reaction occurs by simple nucleophilic attack on the carbonyl group of the thiol ester followed by loss of the better leaving group on the thiolate anion. Then the process is repeated at the second OH group where an unsaturated fatty acid, perhaps oleic acid, is added by the same mechanism. The third acylation requires the phosphate to act as the acylating agent and a polar alcohol to be introduced to form a phosphate ester. This reaction actually occurs by the activation of the phosphate as a pyrophosphate. Pyrophosphates are really acid anhydrides, so it is not surprising that they act as acylating agents. The first step is a reaction with cytidine triphosphate (CTP), doing a job we might expect from ATP, adenosine trimonophosphate. Nucleophilic attack by phosphate group of the phosphoglyceride at the point indicated on CTP gives the pyrophosphate required for the acylation step. The anhydride is now attacked by an alcohol acting as a nucleophile. The attack occurs only at the electrophilic phosphorus center further from the nucleotide. This is an impressive piece of residue and is presumably controlled by the enzyme. The third chain is rather different from the other two. It's a phosphate diester. And the alcohol portion can be inositol joined through the OH group at C1, or it can be the amino acid serine joined through its OH group. The compound formed from serine is particularly important as it can be transformed into the most dramatically contrasted of these phospholipids. A decarboxylation using a coenzyme, we shall look at the mechanism of this reaction in chapter 51, gives a very simple molecule, phosphatidyl ethanol amine. Finally, 3 methylations on the nitrogen atom by SAM gives the zwitterion phosphatidyl choline. Choline is a tetraalkyl ammonium salt and is important elsewhere in biology. Phospholipids form membranes spontaneously. The choline terminus of the molecule is very polar indeed. Phosphatidylcholine adopts a shape with the non-polar chains R1 and R2 close together, and it should be clear that this is an ideal molecule for the construction of membranes. We have already seen how oils such as glyceryl trioleate form thin layers on water, while soaps from the alkaline hydrolysis of glycerides form micelles. Phosphatidylcholine forms yet another structure. It spontaneously forms a membrane in water. The hydrophobic hydrocarbon chains lines up together on the inside of the membrane with the hydrophilic choline residues on the outside. This is just a small piece of a cross section of the membrane. These membranes are called lipid bilayers because two rows of molecules line up to form two layers back to back. The charged hydrophilic region on the outside is solvated by the water, and the hydrocarbon tails are repelled by the water and attracted to each other by weak forces such as van der Waal attractions. Full structural analysis of real cell membrane reveals a chemically diverse thin sheet composed of phospholipid bilayers penetrated by glycoproteins containing the amino sugars we discussed earlier. The amount of each component varies, but there is usually about 50-50 phospholipid protein, with the protein containing about 10% sugar residues. The phospholipids' main role is as a barrier, while the glycoproteins have the roles of recognition and transport. Bacteria and people have slightly different chemistry. We have many times emphasized that all life has very similar chemistry. Indeed, in terms of biochemistry, there is little need for the classification of mammals, plants, and so on. There is only one important division into prokaryotes and eukaryotes. Prokaryotes, which include bacteria, evolved first and have simple cells with no nucleus. Eukaryotes, which includes plants, mammals, and all other multicellular creatures, evolved later and have more complex cells including nuclei. Even much of the biochemistry on both sides of the divide is the same. When medicinal chemists are looking for ways to attack bacteria, one approach is to interfere with chemistry carried out by prokaryotes, but not by us. The most famous of these attacks is aimed at the construction of the cell walls of some bacteria that contain unnatural R or D amino acids. Bacterial cell walls are made from glycopeptides of an unusual kind. Polysaccharide chains are cross-linked with short peptides containing R-alanine, D-alanine. Before they are linked up, one chain ends up with a glycine molecule and other with D-alanine, D-alanine. In the final step in the cell wall synthesis, the glycine attacks the D-alanine sequence to form a new peptide bond by displacing one D-alanine residue. The famous molecule that interferes with this step is penicillin. Though this was not even suspected when penicillin was discovered, we now know how penicillin works. It inhibits the enzyme that catalyzes the D-alanine transfer in a very specific way. It first binds specifically to the enzyme, so it must be mimic of the natural substrate. and it then reacts with the enzyme and inactivates it by blocking a vital OH group at the active site. If we emphasize the peptide nature of penicillin and compare it with D-alanine, the mimicry may become clearer. Penicillin imitates D-alanine and binds to the active site of the enzyme, increasing the OH group of a serine residue to attack the reactive strain beta-lactam. The same OH group of the same serine residue would normally be the catalyst for the D-alanine cleavage used in the building of the bacterial cell wall. The reaction with penicillin protects the serine and irreversibly inhibits the enzyme. The bacterial cell walls cannot be completed and the bacterial cells literally burst under the pressure of their contents. Penicillin does not kill bacteria whose cell walls are already complete, but it does prevent new bacteria being formed. You have seen many instances in this chapter of the importance of a good understanding of both the chemistry and the biochemistry of living things if medicine is to advance. It is at the frontier of chemistry and biology that many of the most important medicinal advances are being made. Problems. Do you consider that thymine and caffeine are aromatic compounds? Explain. Number 2. It is important that we draw certain of the purine and pyrimidine bases in their preferred tautomeric forms. The correct pairings are given early in the chapter. What alternative pairings would be possible with these minor tautomers of thymine and guanine? Suggest reasons why the major tautomers are preferred. Question number 3. Dialkyl phosphates are generally hydrolyzed quite slowly at near neutral pH. But this example hydrolyzes much more rapidly. What is the mechanism and what relevance has it to RNA chemistry? Question number 4. Primary amines are not usually made by displacement reactions on halides with ammonia. Why not? The natural amino acids can be made by this means in quite good yield. Here is an example. Why does this example work? Comment on the state of reagents and products under the reaction conditions. What is the product and how does it differ from the natural amino acid? Question number 5. Human hair is a good source of cystine. The disulfide dimer of a cysteine. The hair is boiled with aqueous HCl and HCO2H for a day. The solution concentrated and a large amount of sodium acetate added. About 5% of the hair by weight crystallizes out as pure cysteine alpha D minus 216. How does the process work? Why such a high proportion of hair cysteine? Why is no cysteine isolated by this process? What is the stereochemistry of cysteine? Make a good drawing of cysteine to show its symmetry. How would you convert the cysteine to cysteine? Question number 6. A simple preparation of a dipeptide is given below. Explain the reaction drawing mechanism for the interesting steps. Which steps are protection, activation, coupling and deprotection. Explains the reasons for protection and the nature of the activation. Why is the glycine added to the coupling step as its hydrochloride? What reagents would you use for the final deprotection step? Question number 7. Suggest how glutathione might detoxify these dangerous chemicals in living things. Why are they still toxic in spite of this protection? Question number 8. Alanine can be dissolved by the following method using a pig kidney acylase. Draw a mechanism for the acylation step. Which isomer of an alanine acylates faster? In the enzyme catalyst reaction, which isomer of the amide hydrolysis faster? In the separation, why is the mixture heated in acid solution? And what is filtered off? How does the separation of free alanine by dissolution in ethanol work? If the acylation is carried out carelessly, particularly if the heating is too long or too strong, a byproduct may form that is not hydrolyzed by the enzyme. How does this happen? Question number 9. A patent discloses this method of making the anti-AIDS drug T4T. The first few stages involve differentiating the 3 hydroxyl groups of 5-methyluridine as shown below. Explain the reactions, especially the stereochemistry at the position of the bromine atom. Suggest how the synthesis might be completed. Question number 10. Mannose usually exist as the pyranoside shown below. This is in equilibrium with the furanoside. What is the conformation of the pyranoside, and what is the stereochemistry of the furanoside? What other stereochemical change will occur more quickly than this isomerization? Treatment of mannose with acetone and HCl gives the acetylsone. Explain the selectivity. Question number 11. How are glycosides formed from phenols in nature or in the laboratory? Why is the stereochemistry of the glycoside not related to that of the original sugar? Question number 12. Draw all the keto and enol forms of ascorbic acid, vitamin C. Why is the one show the most stable? Ascorbic acid reduced form of vitamin C. Question number 13. Caustic soda NaOH was used to clean ovens and clear blocked drains. Many commercial products for these jobs with fancy names still contain NaOH. Even concentrated sodium carbonate Na2CO3 does quite a good job. How do these cleaners work? Why is NaOH so dangerous to humans, particularly if it gets in the eye? Question number 14. Bacterial cell walls contain the unnatural amino acid D-alanine. If you wanted to prepare a sample of D-alanine, how would you go about it? Hint. There is not enough in bacteria to make that a worthwhile source, but have you done problem 8 yet? Thank you.